Okay, class. So, next naman natin di-discuss is the Wien Bridge Oscillator. So, a practical oscillator uses an op-amp and RC bridge circuit with the oscillator frequency set by the R and C components. So, the figure shows a basic version of Wien Bridge Oscillator circuit. So, note the basic bridge operation natin. So, kung napansin, medyo kahawig siya nung bridge rectifier natin. That is because the circuit is arranged nga in such manner. So, itong RNC components natin ng to class, R1, C1, and R2 and C2, ito yung ating mga components which sets the frequencies and also sets our feedback gain. And itong R3 naman to, tsaka R4 na to, ito naman yung nagsiset ng ating parameters ng ating op-amp. Ayan. So, resistors R1 and R2 and capacitors C1 and C2 form the frequency adjusting elements, and resistors R3 and R4 form part of the feedback path. So, this is, yun yung sinabi ko lang din kanina. So, the op-amp output is connected as the bridge input from points A to C. So, yung point na to, tsaka yung point na to, this serves class as your bridge, kumbaga. And this is the output of your, or connected yung output mo dito sa point na to nung circuit natin. Tapos, the bridge circuit output at points B and D naman, B and D, yun naman yung nagsiserve na input dun sa ating op-amp. So, kung baba natin kasi natin tong figure na to, ganito yung magiging itsura niya. So, this is your op-amp. This is your inverting input. This is your non-inverting input. So, gawin muna natin yung R3 tsaka R4. So, sa negative class, dyan nakakonect yung ano ba naman yan? Ayan, so, ayan, dyan sa negative, sa inverting input nating class, dyan nakakonect yung R4 mo na nakakonect sa ground. Tapos, yung R3 mo is nakakonect sa, this is your R4. Tapos yung R3 mo is nakakonect sa output natin. So, this is your R3. So, kung napansin, meron tayong R4 nakakonect sa ground, R3. This is similar to a non-inverting amplifier. Next, also, from your output is connected din dito sa point A, yung transistor circuit, yung RC circuit natin. So, from your output, may nakakonect ka na capacitor C1, tapos ano ba dapat? Yan, so nahirapan ako mag-drawing. Ano ba yan? Ayan, capacitor C1. Tapos, yan yung resistor natin, R1. And then, may nakakonect sa kanilang parallel na R1, R2, tapos C2. Tapos, nakakonect sa ground. Tapos, nakakonect sila sa non-inverting input natin. So, kung i-redraw natin yung circuit class, ganito pala yung kakalabasan niya. So, ito yung sinasabi nating part kanina that your R3 and your R4, a portion of your output is being fed as isa part of the feedback network papunta doon sa input ng op-amp mo. And then, the R1, C1, and R2 and C2, sila naman class yung part ng circuit natin kung saan siya yung mag-cause ng frequency adjustment natin. So, kung napansin kasi, ito yung circuit natin kanina. Similar siya din sa circuit kanina ng IC, except that, in this case class, this is itong IC phase shape oscillator natin, this is inverting, tapos ito yung RC networks natin. But for the Wien Bridge class, ang RC network natin is just dalawang set of Rs and Cs, tapos yung R1 RC natin, series, R2 RC natin, R2 C2 natin is parallel. Tapos, aside from that, this is non-inverting. So, yung input natin is nakapasok sa positive, sa non-inverting input and not to the non-inverting input natin. So, but in a sense, parehas lang siya talaga. Kung hawig lang talaga siya nung IC phase shift oscillator natin. Ayan. Now, for the computation nito, class, ito huwag muna natin itong pansinin. Baka kasi makadagdag na dito sa inyo. Ang tingnan na lang natin dito, class, is for the oscillator frequency class, using just the formula of oscillator frequency and what we know about RLC circuit. So, we have an oscillator frequency of 1 over 2 pi times R1 times the square root of R1, C1, R2, C2. Now, if ang ating R1 at R2 ay same at ang C1 at C2 natin ay equal, so we can just simplify the formula to our oscillating frequency is equal to 1 over 2 pi RC. Now, yung dapat daw na value ng R3 tsaka ng R4 natin is equal to 2. Now, what we have to know din pala with this circuit is that this RC circuit, this introduces a feedback gain of 1 over 3. So, therefore, yung beta mo dito, class, is 1 over 3. In short, kapag dumaan yung signal mo sa RC circuits natin na to, sa RC network mo, bababa yung kanyang signal or value by a factor of 3. So, kung bababa to by a factor of 3 to ensure oscillation, dapat yung A mo would be greater than 3 dapat. So, that is one condition that we need to meet. So, mas mataas to dapat sa 3. Now, paano ba natin makukuha yung A mo dito? Yung A mo dito is nakadepende sa R3 mo tsaka sa R4. To be specific, this is a non-inverting amplifier. So, therefore, yung A mo is equal to 1 plus RF over Rin. Wherein in this case, ang RF mo is R3 and yung Rin mo is R4. So, therefore, we will have 3 at least is equal to 1 plus RF mo is R3 over R4. So, ang R3 mo over R4 is equal to 2. So, ibig sabihin, the ratio of your R3 with R4 should at least be equal to 2. So, that is to ensure na meron tayong oscillating action na mangyayari. Example, calculate the resonant frequency of the Wien-Bridge oscillator of the figure. So, to get that, napakadali. We know the values of our capacitors and our resistances. So, we can just substitute directly to the equation. Since parehas lang naman sila ng value, let's use 1 over 2 pi RC. And we will arrive at 3,120.7 Hertz. Another example, so design the RC elements daw for a Wien-Bridge oscillator for operation of FO is equal to 10 kilohertz. So, palitan daw natin yung mga R's natin tsaka mga C's natin para mag-arrive tayo at an FO of 10 kilohertz. Yeah. Now, for this kinds of problem class, what we have to remember dito ay nagde-design tayo. So, kung nagde-design tayo, at some point, we have to decide ano ba yung mga parameters natin. Kasi for this one, whereas for the RNC elements. So, kung RNC yung elements na kailangan hulaan mo or di hulaan. You need to think of a good value for your R or for your C and then use that value to find the value of the other. So, ganun yung gagawin natin. So, papansin nyo naman yan pag ang sabi sa tanong ay design. So, ang gagawin nyo, you will need to think of your own values muna. So, may konting freedom tayo to find the value. So, for this one, let's use a value of R na 100 kilo. So, if 100 kilo yung gagamitin mo, syempre, ano ba yung mga considerations natin for choosing the value of R? Syempre, gusto natin yung available na sa market. Alangan namang maglalagay ka na lang ng resistor, ang lalagay mo pa is yung hindi pa makita sa market, di ba? So, para maging mas madali at practical, ang ilagay mo na yung available sa market. Like, let's say, for example, ay 100 kilos. Now, if you already use that, 100 kilos as your R, you can now find the value of C. Now, ang C natin is apply lang natin dun sa formula, then take the value of C. We will arrive at 159 picofarads. That is our value of C. So, therefore, papalitan lang natin ito ng 100 kilohms. Ito, 159 nanofarads. Ito, 100 kilohms. And this is also 159 nanofarads. And that is already our design or new design for the RC elements. So, that is considering, syempre, na yung R3 at yung R4 natin, we will still use yung kanina. Ang malaga lang naman dito is yung R3 natin, tsaka ratio of R3 over R4 is greater than 2. In this case, this is 300 over 100. That's 3. So, that is greater than 2. So, that is an acceptable value. Yeah, next, we have tuned input and tuned output oscillator circuits. So, a variety of circuits class can be built using that shown in the figure by providing tuning in both the input and output sections of the circuit. So, when we tuning in, kumbaga parang sinutune natin or both the input and the output side, naglalagay tayo ng circuit to tune it in a frequency or in a phase na gusto natin. So, di ba, ang gusto nga natin mangyari is may phase tayo na makuha 180 degrees may 180 degrees na phase shift tayo. So, we get that phase shift by tuning in both the inputs and the outputs. So, ito yung general na circuit niya. So, we have amplifier and then we have 3 reactances, X1, X2. Yung X1 nakakonect sa input, yung X2 nakakonect sa output, and another one na reactant which is X3. So, with this kind of circuit, pag iniba-iba natin yung components for your reactances, we can have various types of oscillator. So, ito yung kanyang table. So, if your X1 and X2, ang gagamitin mong reactance elements are capacitors and yung X3 mo ay inductor, you will have a Colpitts oscillator. So, ang palatandaan ko dyan nung nagre-review ako sa board is Colpitts. So, C. So, sabihin, capacitor yung reactance elements ng input and output mo. Yun. Next is Hartley oscillator. So, alam ko lang, pag Hartley oscillator, excuse me, pag Hartley oscillator, hindi siya yung Colpitts. So, kung hindi siya yung Colpitts, ibig sabihin, inductor yung gamit niya sa kanyang mga reactance elements sa input and output. Tapos sa output naman is capacitor tayo. And next, we have the tuned input and tuned output. You use both LC circuits on X1 and X2 as your reactance elements. So, Colpitts oscillator muna tayo. So, this is an FET or a FET Colpitts oscillator. So, sinusundan lang niya yung figure natin kanina, but in this figure class, ito yung ating op-amp kumbaga. And then, this is your reactance elements. This is your X1, this is your X2, this is your X3. And for this class, the oscillator frequency can be found to be this one. That is, ano lang din to, formula lang ng oscillator ay ng resonant frequency. That's 1 over 2 pi times the square root of L times CEQ. So take note, yung capacitance natin dito is a combination of your C1 and C2. And yung CEQ natin is C1 times C2 over C1 plus C2. So ito lang yung kailangan nating tandaan. Now actually, kung titingnan nyo dun sa circuit, halos mapapansin natin that C1 and C2, kung consider natin to as one circuit, they are magkatabi. Kung magkatabi sila, series sila sa isa't isa, kapag kinuha natin ang capacitance ng series na capacitors, ganito natin siyang kinukuha. So, kung baga, pwede natin siyang, kung alam nyo lang yung concept ng kung paano kinocompute yung total capacitance. Kahit hindi nyo natandaan to, tandaan nyo na lang. Basta alam nyo kung paano siya isolve. So, but anyway, yun, ganun yung formula natin. Now, pwede na instead of FET, we use BJT. So, like this one. Still, the oscillator frequency is equal to 1 over 2 pi LCE, square root of LCEQ. And yung LCEQ natin still is C1, C2 over C1 plus C2. You can also use an IC. And ganun pa din. Kung IC yung gamit natin, iyan pa rin yung X1 mo, X2, this is your X3. Yung iyong oscillator frequency is still 1 over 2 pi square root of LCEQ. Yeah. Next naman is the Hartley oscillator. So, para rin siyang Colpitts except that imbis na capacitance, meron tayong inductor na gamit. But take note class, in the inductors natin, sa L1 and L2 natin, they have a mutual coupling M which must be taken into account into determining the equivalent inductance. Diba? Remember in your, I don't know, electromagnetics ba to? Ang inductors natin class, when we find the equivalent value of the inductors, we need to consider if they have coupling. So, kung may mutual coupling ba yan or depositive yan, tapos kung may hindi mutual yung coupling, that's negative 2M, basta ganun. So, kailangan consider natin yon. Now, for the resonant frequency or the oscillator frequency class, that's just, again, equal to 1 over 2 pi LC. But yung L natin dito is a combination of L1 and L2 considering the mutual inductance. So, yung EQ natin dito is L1 plus L2 plus 2M. We can also use a transistor instead, a BJT instead of an FET. So, parang sa Colpitts lang din. Hindi na nakalagay dito, but you can also use an IC. But in all configurations, the resonant frequency is always this one. Yan. And lastly, we have the crystal oscillator. So, ang crystal oscillator natin class is basically a tuned circuit oscillator using a piezoelectric crystal as a resonant tank circuit. So, the crystal, which is usually quartz class, it has greater stability in holding constant at whatever frequency the crystal is originally cut to operate. So, ginagamit natin itong mga crystal oscillators class for applications na kailangan ay stable yung ating pinoproduce na frequency. Like sa radio systems, so kailangan dyan ang carrier frequency mo ay stable. Kasi kapag nag-iba yung carrier frequency mo, yung output signal mo will be different. So, hindi na siya magiging accurate. And then, baka mamaya, hindi ka na nakatune at the frequency kung saan gusto kang pakinggan ng mga listeners mo. So, that's very important na stable tayo doon. Now, paano nga ba nag-work yung crystal oscillator? So, ang nangyari lang nito class is because, ayun nga, of the piezoelectric effect. So, nangyari nito class, kapag may mechanical stress kasi tayo na ina-apply sa isang quartz na crystal, so, nagkakaroon tayo ng potential difference between the phases of the crystal. And that potential difference class, nagkakos yun ng electricity. So, yun, nagkakos yun natatransform yung mechanical stress into electronic signal. Kaya nga, piezoelectric effect yung tawag natin. Now, similarly, kapag naman voltage yung in-apply mo, so, magkakaroon naman siya ng mechanical distortion or magkakaroon siya ng mechanical movement naman. So, yung movement na yun class or yung mechanical stress na yung class or yung electricity or potential difference na mapo-form din sa crystal natin, they would be at its natural frequency or natural resonant frequency. So, when alternating voltage is applied to a crystal, so mechanical vibrations are set up, and these vibrations will have a natural resonant frequency. Depende sa crystal mo. And that resonant frequency class is very stable. And mag-work yung crystal mo or the form, yung mafo-form mo na mechanical vibration or mechanical stress will be very consistent. So, parang sa ano lang, di ba yung mga nakapanood na kayo ng mga wine glass, tapos binabasag siya ng gamit yung boses. So, ang ginagawa lang doon, class, is may acoustical energy na fino-form, that is yung boses natin. Tapos, sineset natin siya or kinakanta natin or nagbibigay tayo ng note kung saan high ay equivalent yon sa resonant frequency nung ating wine glass or ng ating object. So, kung makapag-produce tayo ng sound, physical energy, na ganun yung frequency niya, tapos tatama yun dun sa object natin, tendency class, magpa-vibrate yung object natin. At kapag nag-vibrate yung object natin, nabibrake siya. So, ganun din yung mga mechanical, or ganun din yung mga crystal oscillators natin. Now, to represent the operation of a crystal, of a quartz crystal, parang ganito class yung equivalent niya. So, we have this crystal oscillator. Ang equivalent niya class is an LC circuit with a shunt capacitance CM. Ayan. So, yung R natin class, that is the internal friction. It is equivalent or analogous to the, kumbaga na lang to, representation. So, this resistance R class is equivalent to the crystal structure's internal friction. Yung L and C naman class, L is the crystal mass and C capacitance naman is equivalent to the compliance. And yung CM naman class, this is due to the mounting of the crystal doon sa ating circuit. Siyempre, pag minount mo yan, balot yan ng dielectric kumbaga. So, magkakaroon siya ng capacitance. So, ito yung equivalent niya class. Ayan. So, that is it for this chapter. Ayun. So, ang kailangan lang talaga nating tandaan is the very basic principle of feedback circuits. Now, number one, if you have a negative feedback, you have an amplifier. Next, if you have a positive feedback, you have, or you may be able to make your circuit or op-amp work as an oscillator. Ayan. So, that's it.